Woohoo! Welcome back. Today we're going to be using implicit differentiation to take derivatives with a Lemniscate. Woohoo! So first things first, you want to pause this video and make sure you have something that's to drink, maybe a little snack. You've got a comfort or support animal or person or stuffed animal or piece of chocolate, whatever it is that keeps you calm, because some of this is going to be pretty intense and it's all going to turn out great. You're going to see that it's totally doable, but when we get in the middle of it, it's going to feel a little bit intense. So just prepare for that. But we're totally going to do this and it's going to be totally cool. So here we go. Woohoo, Lemniscates. So what the heck is a Lemniscate? I don't even know if I'm saying it right. It's been so long since I've heard anyone say it, but let's hope I am. Fingers crossed. Basically, it is a figure 8, and this is the graph. And if you're wondering, could we do this on Desmos? We could totally do this on Desmos, but the problem is my camera that's right there is actually my cell phone. So that's how it would show you Desmos. So you're going to have to imagine I'm showing you that you can just type this in directly to Desmos. And then if you want to play with it, kind of play around with different versions, change this number, the 2 and the 25, and see what happens. Because as these two numbers change, the figure 8 will get bigger and smaller. Like that. And there are other ways to change it. You're welcome to do a deep dive. But for us today, we're just going to use it as an example of a very complicated looking creature. So from the beginning, if we look at this and I say, well, what do we do if we want to find the derivative? And specifically, we want to find y prime. Hopefully, just a quick look at this says, oh, this would be so complicated to untangle and get the y out. So finding an expression that says y equals seems difficult, if not impossible. So we're not going to use standard differentiation. We're going to use implicit differentiation. And basically all that means is we can take the derivative right as it comes to us. We don't have to change it. Like, this is really the way you want to do it. If someone comes to you and says, hey, you want to go to coffee? You don't say, yeah, but first you got to change your clothes and change your name. And I don't like the way your knees look and that sort of thing. So this is a way of saying, yeah, let's go to coffee just as you are. So we're going to go to coffee. So what does the problem say? Find the points on the Lemniscate, this guy in blue, where the tangent is horizontal. Now, I copied a picture of the graph so that we could go in and say, okay, horizontal looks like that, right? That's horizontal. What else do we know about that? What is the slope? The slope is 0. So basically, what do we want? We want the derivative dy dx, or just simply y prime, to be 0. Oh, sorry, that's off the side. You can't quite see it. There we go. Woohoo. But where would that happen on this graph? And if you take a look, I see 4 places. Now, not to scale, but I'm going to guess somewhere right around here, somewhere right around there, somewhere right around there, and somewhere right around there. Each of these places, the tangent line. Oh, look at that straight line. Yeah. Oh, well, so I'm not doing very good with the straight part, but you got an idea of what it's supposed to look like. Basically, it's supposed to be a flat line like that. And there are going to be 4 places. So right off the bat, sorry about wiggling the table. Right off the bat, we know we're expecting 4 answers. Okay, you guys ready? This is very cool. Now, if you want to pause here for a moment, you might want to pause. Play with Lemniscates a little bit. Make friends with them. Look them up. Wikipedia has an amazing article all about them. And we can also, you and I just standing here, sitting here, whatever you're doing yoga, whatever you're doing to watch the video, we can appreciate that when we see a bunch of x squareds and y squareds, we expect things that look like circles or parabolas or ellipses. Now, obviously, this is something more complicated with squares inside squares, but it kind of reminds me of those curvy things like circles or parabolas or hyperbolas or ellipses. So that doesn't seem that far off. So we're going to take a moment, and believe it or not, I have to let my kitten in because my kitten is panicking. She said, don't start the video without me, but then I couldn't find her. So just a moment. Think of the Lemniscate. Sorry. Come on, Fisky. Come on. Denied. Oh, I fell for the oldest kitten trick in the book. She didn't want to see the video. She wants me to go outside and play with her, which I will do later. Okay, Fiskid. Yeah, you go play. Okay. You guys ready? I think I've stalled enough. You ready? Okay. So remember that when you're... Oh, this is going to get exciting. She's here helping. Come on. Hop down, hop down. Okay. You sweet. Seriously? This is what we're going to do? Okay. She's trying to help you out. She's like distracting me and she's saying, run, you guys run, avoid the implicit differentiation. She was trying to help you out, but I'm just going to keep going. I cannot be dissuaded. I can be distracted, but eventually I'll come back. Okay. I've got 2 times the quantity x squared plus y squared, the whole thing squared, equals 25 x squared minus y squared. Okay, that's the original equation. Now, implicit differentiation says that I just go in and I just approach it as it comes to me. So when I take a derivative, this is going to involve the chain rule a bunch of different times. So first things first, if I've got a constant out in front, but it's multiplied times something with variables in it, I just bring the 2 down. So this 2 is just going to come down. Next thing, I see these, but they're inside a squared. So I'm going to do the squared first. So this 2 is going to come down in front. I've got the exact same inside, the x squared plus y squared. No derivative, plain version. And then I do 2 to the negative 1. That's the outside. Then I have to take the derivative of the inside, which I will do in the next step. Over on the other side, I've got a number out in front. This coefficient just sits there. 25 waits for us to do what we need to do. And then I'm going to take the derivative of x squared minus y squared, right? Because it's going to be a straight up derivative. Yes. She's just agreeing. This is the way to do it. So now let's see. I've got 4 times the quantity x squared plus y squared to the first power. And then I have to do this derivative. Okay. So what does this derivative look like? Well, I'm going to take the derivative of x squared. That's going to give me 2x. And now there are 2 ways to do this. Some people just say when you take the derivative of x, you just put in a 1. But I learned that you do, the 2 comes down, right? You do 2 minus 1, and then you make the point that you just took the derivative of x with respect to x. I'm going to do the same thing with y. Y squared, the 2 comes down, y to the 2 minus 1 times, and this time I took the derivative of dy dx. Okay, over on the other side of the equals, I've got a 25, and I'm going to do exactly, it's going to look just like this, but it has a minus in the middle. She's really trying to help you out right now. She is trying to make sure you guys don't suffer any more than you need to. So the 2 comes down, 2x to the 2 minus 1, and then I note that I took the derivative of x with respect to x, because I was doing an x, minus 2y to the 2 minus 1 times dy dx, because I was taking the derivative of y. Okay, so let's take a look if I can make this look pretty. I've got 4 times the quantity x squared plus y squared, and then I've got 2x, 2 minus 1 is 1, dx dx, this is also 1, right? So I've just got 2x sitting here. Then I've got plus 2y, 2 minus 1 is 1, and then dy dx. over on the other side. Oh my goodness. Can I make this any bigger? There we go. Can I do that? Can I shift this ever so slightly so I can get everything in? There we go. And then over on this side, I've got 25. And then I've got 2x. And remember again, dx, what's the derivative of x with respect to x? Is just 1. And then minus 2y dy dx. So notice what happens. In implicit differentiation, we are assuming y is a function of x. We're assuming x is just a variable. So when we take the derivative, nothing fancy happens. But when we take the derivative with a y, we have to remember the chain rule and take the derivative of y with respect to x. Now, I'm going to note that some people, I'm doing it, using this Leibniz notation. There's another way to write it, if you prefer, that's going to look identical. But instead, you're going to write 2y times y prime, and then 25 times 2x minus 2y times y prime. They are effectively the same. I mean, they're not the same notation, and there are benefits to each. But for your purposes, you could choose to do either one. I don't think that there's a preference one way or the other. Okay. So now we have to stop and see what the heck we've done. We went from the equation that describes this wonderful figure 8 shape, and we used implicit differentiation. We differentiated on the left and the right, and then we ended up with this expression, this equation, that has derivatives in it. Okay, so now what? Well, now we have to go back. Before I lift this up, we're going to use this right here, the fact that we know that if the tangent is horizontal, the derivative of y with respect to x is 0, right? The slope is 0. So that means, if I can get this kind of set up in the camera, there we go, that we've got 4 times x squared plus y squared times the quantity 2x plus 2y. And now where there was a dy dx, I'm going to put in a 0 because that's 0. Now, if we were looking for all the places where the tangent had a slope of 1, I would plug in 1. We could look for all the places where the tangent had whatever slope you're interested in. We would just plug that in there, and then another one right there. So then over here, I've got 25 times 2x minus 2y times 0. Again, because this is where the derivatives are. So here's the thing. A lot of people assume, especially if you've been going through math, if we know that the derivative of y with respect to x is 0, we have to solve for that and set it equal to 0. We don't. We just plop the zeros in wherever they already are. Like I said, we're not making any demands of this equation. We're like, just come to lunch. We can all have a good time. We can figure out where your tangents are horizontal, as you do among friends. So now what? Well, the nice thing is, fingers crossed, with zeros, that makes terms disappear. So I've got 4 times the quantity x squared plus y squared times, and notice that this is going to be 0, so the whole thing is times 2x. Suddenly the left-hand side is a lot less complicated. Over on the right-hand side, I've got 25 times, and then again, this term is 0, just times 2x, which is pretty cool. Now, the trick here, I'm sorry, this is an equals equation. So these should be arrows, not equals. I apologize. Otherwise, it's confusing. It's like a run-on sentence. Okay, now this part is the part where you have to kind of have an idea of how these things work to know what the next step is. And I happen to know how these things work because now we have a much simpler equation, but there's still a lot of stuff going around. And a lot of people would be like, okay, now I have to solve for y. And the answer is no, we're not going to solve for y. We want this to be true. So when is this true? Well, it's true when this bunch of things equals this bunch of things, right? When these two things are equal, then we get those horizontal tangents. So I'm going to play with this equation, and I'm going to say over here on the left, I actually have 8x times x squared plus y squared. Now over on the right-hand side, I've got 50x. And again, I'm going to encourage you to not go right into multiplying out. Yes, you're absolutely welcome to, but you don't need to in this case. What I'm going to do is I'm going to subtract 50x. I'm going to put everything on the left. Now, could you put everything on the right? Absolutely. Now, why did I go to this trouble? Well, if you subtract everything from the side, you get 0. And if you've got 0 in an equation, then you've got the option or the possibility of the option of my favorite property. Of course, I have a favorite property. Of course, you should have a favorite property too. Can I recommend this one? It's a very cool one. It's the 0 property, my favorite one. So what does that mean? Well, if I look through this, I got a big bunch of gunk right there. But I got an x here, and I got an x here. And in fact, I got some 2's running around. So what I'm going to do is I'm going to factor out a 2x. Oops. And in fact, I want to use brackets because this is going to get jiggy. Okay, let's factor out the 2x. Then I've got 4. And this big gob of goo, whatever we're going to do with that, we're not going to worry about that yet. We're just going to say it'll take care of itself. And when I factor out 2x out of minus 50x, I get minus, you got it, 25. And then I've got two things multiplied together to give me 0. The 0 property says, if a times b equals 0, then a equals 0 or b equals 0. And the nice thing about or in math is that or means they could both be true. So it's possible they're both 0. So one of them is 0 or the other is 0. Basically, it says if this thing times this big gob is equal to 0, one of them had to start with 0. You can't just make a 0 out of nothing. See what I did there? But zeros cannot be created. They just exist. So this means that either 2x equals 0 or 4 times the quantity x squared plus y squared minus 25 equals 0. And I know you're all thinking, oh, thank goodness, because that's exactly what I was thinking. Stay with me. If you need to, this is a long video. It's going to be pretty long. It's going to be one of my longest because it's going to take a while. So if you need to, take a pause, take a break. No shame in that. You know, shake out the limbs, go touch some grass, look at the sky, go scream about how calculus makes no sense or that calculus is awesome. You know, do what you need to do and then come back. I'll wait. Okay, I'm waiting. Go on. Pause. Come back. Okay, you back? Woohoo! Yay! Okay, so let's come back to the very tiny graph, which I feel is suddenly very, very small. So one of the possibilities is 2x equals 0. So that means x equals 0. Where does x equal 0? X equals 0 is right here. All right, it's right at this point. Is the tangent horizontal there? And the answer is no. I can see that, right? I don't have a better one. So if we look at the slope coming in, the slope right here is kind of like this, almost -1 maybe, coming around there. And if it comes up from here, again, this is like a slope of like 1. So there's no flat horizontal tangent there. So is math mean? Is it lying? No. Math is saying if we have x equals 0, that would make all of this stuff make sense. And we say, yeah, it would make it make sense, but it's not the point we're looking for. We're looking for these points right here, whatever these values of x are, that'll give us these horizontal tangents. Okay, so x equals 0, although the math would work, it's not quite right. so like if you get invited to a wedding and the wedding invitation says you get a +1, I mean, technically you could bring your favorite bunny rabbit, but it might not be the +1 that the people who are inviting you were imagining. It might be great, it might not be. So it depends on the situation. This x = 0 is not a helpful situation. It's not a helpful answer for us. So we're going to say, yes, it would make all this work out, but it's not the solution for this situation. So now, okay, so now we're on the big gob thing. And at this point, if you're still with me, congratulations. This is a lot of work. This is kind of one of those situations where you have to step out into the darkness, not knowing what you're going to step on. Hopefully it's just a pathway that's just very dark and it's not like anything sticky. Unless you like sticky, go for sticky if you like it. So we've got this equation. I'm going to go ahead and see what sort of interesting things I can come up with. And one of the things I can do is I can add 25 to both sides. And another thing I could do is I could divide both sides by 4. Ooh, I tried to put the 4 up on top. Sorry about that. Yeah, my brain likes to skip steps. And then suddenly, hopefully, you're like, whoa, this is going to describe a whole bunch of points that would all work. X squared plus y squared equals 25 over 4. That's a circle. And I'm going to guess that it's this circle that would go through all 4 of these points, right? But that's going to give us a bunch of points that aren't the ones we're looking for. And this is somewhat frustrating, right? So we're like, okay, now what? We've got a bunch of points, but we know that we're just looking for 4 of them. Which ones are they? Ugh, right? Am I right? So this is then what we're going to do. And I want to go through this problem because it's so many steps, and I don't know who the first person was who started working with these, but I know for me, if I hadn't have been through it, walked through a problem that's like this before, I'd have no idea. I'd be like, oh no, what do we do? Oh no. But what I'm going to say is don't panic. Don't panic. We have got a great equation. I'm going to mark it as equation number 1. It is this circle, which is really cool. Okay. So then, after we've got that, I'm going to go ahead and write it up here on this page. We've got the equation x squared plus y squared equals 25 over 4. Okay. So now I want to go back to this. Sorry, how do I do this? This graph and this equation. And I know that this is the equation of a bunch of points that make up a circle, right? X squared plus y squared equals 25 over 4. In fact, the radius this is r squared, so it's 5 halves, so it's 2.5 point, And then you've got the Lemniscate that goes like this. Not to scale. And already we're getting some really cool imagery here. And what I want to do is I want to find just those 4 points. Those are the ones I'm interested in, right? Not all the points. This is the circle. And the Lemniscate, which is 2 times x squared plus y squared equals 25 x squared minus y squared. Let's call that blue because I feel like blue and I've already used green. This equation gives us this guy. We want the 4 points that are on the intersection of these two. And so how do I do that? Well, what I do is I find the intersection of the two, and I use something called substitution. So hopefully you go back way back in algebra and you think, oh, substitution. That means I can take this equation and then I can plug in the fact that x squared plus y squared equals 25 over 4, right? That's what we know from 1. And then we get, let me write here, this is the original equation. And so from the original equation, I get 2 times the quantity 25/4, the quantity squared, equals 25 times x squared minus y squared. Unfortunately, we don't know what x squared minus y squared equals. We only know x squared plus y squared. Okay. Are you still with me? Okay. At any moment, you can pause this. That's the great thing about videos. Go do whatever you need to do and come back. I will wait for you. Even if I'm in the middle of it, and then you can start me right up again, right? So this is great. Take breaks while you need to. This is pretty intense. Okay. Now, I know what I'm aiming for. So at this point, this is going to just seem like a pile of useless information, a bunch of numbers. But I happen to know that I'm interested in looking for what x squared minus y squared is. So I'm going to divide both sides by 25. Okay. Some interesting stuff happens over here. A 25 cancels. So we don't have to work out what 25 times 25 is, although it's 625, but you don't have to know that. And this 2 cancels completely here, but it leaves 2 there. And so we've got 25 over 8 is x squared minus y squared. You guys aren't going to believe it, but we are almost there. I'm going to rewrite this as up. You know what? I'm not going to rewrite it over there. I'm going to rewrite it on the next line. Okay. So x squared minus y squared equals 25 over 8. And I'm going to call this the second equation. And now, and some of you have seen where this is going and the horror, I can just feel the horror descend upon you and spread out through your whole body as you realize, oh my gosh, we use substitution there. We're going to use elimination now. And the answer is, yeah, we're totally going to use the elimination. It's going to work out because we got x squared plus y squared equals 25/4. And x squared minus y squared equals 25/8. And I know you guys woke up this morning saying, ooh, the one thing I really want to do is add fractions, because that's what you do, of course. So over on the left side, I get 2x squared, and over on the right side, we really hope that we've got a calculator, or we do it by hand. 25/4, 25/8, LCD is going to be eighths. So 25 over 4, how many eighths is that? Times 2 is 50 eighths. So we've got 50 eighths plus 25 eighths, and that's 75 eighths. And you're all saying to yourself, great, 30 minutes, are we done? And I say, we're really, really close. We are so, so close. This is amazing. You guys have been very patient. And you can show this to people and be like, look what I can do. And people will be very, very impressed. So I've got 2x squared equals 75 eighths. And you say, oh, yay. And then what are you going to do now? And I'm going to say I'm going to divide both sides by 2. I'm going to actually multiply by 1/2 over on the left. And I'm going to end up with x squared equals 75/16. And then I know you're all like, no, don't do it. I'm going to totally do it. X equals plus or minus radical 75 over 16, which is plus or minus radical 75 over radical 16, which is plus or minus 75 is 25 times 3 all over 4, right? The square root of 16 is 4. And then using bare math or regular math, I'm going to get plus or minus, the 25 sends 2 5s running. Yum, yum, the bear eats 1. And 1 makes it out. So we've got 5 radical 3 all over 4. So x equals 5 radical 3 over 4 or negative 5 radical 3 over 4. Now, we have some options. Very few good options, but we have some options. Once we know what x is, it is possible that if we're very clever, we could plug it into the original equation to find y. It's possible. I'm looking at that thinking, I'm not sure I think that would work for me. I mean, maybe. It's possible. Very, very possible. But if I want to find y, I'm going to go looking for an easier equation. So I'm going to scan everything. And I'm going to see that I do have this x squared plus y squared equals 25/4. And I think that's going to be a little bit easier. X squared plus y squared equals 25/4. Now, am I going to actually square this? No. Because right there, up there, I have x squared. That's 75/16 plus y squared equals 25/4. Okay. Then I'm going to just in situ, because I am so ready to be done with this. This is going to be 100/16. I'm going to subtract 75/16 from both sides. And I'm going to get y squared equals 100 minus 75/16, 25/16. So y equals plus or minus square root of 25. Can you still see it? Yep, over square root of 16, which is plus or minus 5/4. Oh my gosh. But what do? I've got 2 answers for x and 2 answers for y, and yet we started out, what was it, last Tuesday on this problem, and we said there should be 4 solutions. And we look at these solutions and we go, okay, 5 is plus or minus this value. So there's the plus 1, these 2. There's the minus 1, these 2. Y is plus or minus 5/4. So y is these 2 and these 2. Wait, so all I have to do is match each of these with each of these, and I got a full set of solutions. Let me show you what I mean. So, that's not going to fit. So you're going to have to trust me that I'm copying it down correctly. So, if x can be positive 5 radical 3 all over 4, or negative 5 radical 3 all over 4, and if y can be 5 over 4 positive, or negative 5 over 4, then I can actually make 4 combinations. 5 radical 3 over 4, 5/4. So they're both positive. Negative 5 radical 3 over 4, negative 5/4. They're both negative. So I do the plus plus 1, the minus minus 1. And then what are the other 2 then? They're going to be a mix, the plus and the minus, or the minus and the plus. So I'll do 5 radical 3 over 4, negative 5/4, and negative 5 radical 3 over 4, positive 5/4. And oh my goodness, we're done. That's it. That's the solution. Now, why do we care? Well, maybe we don't. From a math perspective, it's just a problem, and we're just going through patterns to solve it. But what interesting things could we be talking about? Well, if this would be a really weird orbit, you'd have 2 planets or something. I don't know. That would be interesting. You know, you can look into lots of sci-fi where you've got 2 planets or 2 suns or 2 moons or something, and there's some weird orbit that's happening like that. And you're interested at what point the, if as you're going around in the orbit, you're heading off perfectly horizontal in terms of, what direction you're headed in, this direction or that direction or vice versa. So I could see that being a solution to like an aerospace situation. I can also see this being a solution if you're actually looking at particles moving around in some sort of space. So you can imagine in the physical world, there could be some really cool applications of this. As far as math is concerned, it's just cool to be able to solve this problem. I do think that this particular problem is a lot easier because we're looking for horizontal, so we're looking for 0. If we were looking for something that were, 1 or 2 or 3 or 4, it may be a slightly more tricky problem. I think we could still do it. But you guys made it. We did it. We did it. We did it. La, la, la. I don't have any puppets to dance with me, so you guys are going to just have to dance. You guys are awesome. So absolutely, it's been 36 minutes. I need to go touch some grass. I need to remember that I'm actually human and not just a math computer. But I'm pretty proud of myself. We made it through. Woohoo! I'm proud of you guys. So get out there, get some air, get some fun, wiggle your body, do something interesting. Go look at some pretty art or dance or find some friends to talk to or read a book or play a video game. But be conscious of the fact that you've been staring at a screen for possibly 40 minutes at this point. And it's not good for your eyes. So give your eyes something else to focus on. Focus on something really far away. Focus on something mid-level. Go pet a cat. Just take care of yourselves and be amazed. We did this. Woohoo, look at all these pages. Oh my gosh, so much math. And I'm very proud of you, and you guys are awesome. And I hope you have a great rest of your day. And woohoo, and math on. And FizzGeek says hi.